Thank you.
Let's continue with the third talk. Please, Lara.
Still me. OK, guys. So I feel that I have to appeal to your patience. So you might say, I'm here for a school on supergravities. You've been talking about geometry for the last hour. Why should I care? The direction that I'm going with all of this is that if we understood how to build all Calabi-Yau's, if we knew whether it was possible, whether there's a finite set, if we understood whether the constructions that I'm writing down are everything, then in principle you could characterize which effective theories are actually possibly realized from string theory. So I want to comment a little bit now on, with these types of simple constructions that I've just shown you, how far can you get? What do you understand about finiteness? And what can you say about the space of string vacua that you're sweeping out? So one crucial thing that I haven't said yet that I need to is, and someone asked this question during the break, which was a great question. I've written down different algebraic descriptions of Calabi-Yau's. How do I know that those two different algebraic descriptions are in fact different manifolds? This is a great question. So if you say how many distinct Calabi-Yau's are there, we can start working this up dimension by dimension. So let's actually try this. Suppose we weren't just interested in four-dimensional theories for a moment. If we look at one complex dimension for Calabi-Yau's, I can write down, for example, this guy, a cubic equation in P2 that satisfies the Calabi-Yau condition. This is a complex one-fold. This would be a Calabi-Yau. I could alternatively write down this guy, P1, P1, 2, 2. Have I just written down two distinct Calabi-Yau one-folds? That would be cool. The answer is, in fact, no. Anything you can write down, and there are an infinite number of descriptions of this type, Calabi-Yau one-folds are, in fact, unique. There's only one, the 2 torus. That is the only thing you get to write down, and you can write down different algebraic descriptions. That's great. 2D, life is still simple. This is the famous K3 surface. This also has an infinite number of algebraic descriptions. For example, P3, 4. This is one equation in a three-dimensional space. That's a Calabi-Yau two-fold. That's just one description of it. This is the unique Calabi-Yau two-fold as a surface as well. As we discussed, some K3s are not even algebraically realized, but it's all still in the same moduli space. So if I was saying how many different supergravities could I get, if I was interested in just dimensionally reducing on Calabi-Yau one-dimensional or two-dimensional spaces, so getting 8 or 6-dimensional heterotic theories, if it was just about the geometry, the base geometry, life would be very simple because there's a unique choice. Even though you write down different algebraic descriptions, still only one. But what happens when we hit 3D? It would be great if there was still just one, and it was really a useful Calabi-Yau. In fact, there are more than a billion distinct Calabi-Yau three-folds known already. So how do I decide that two Calabi-Yau's are in fact different? The way that I decide is by considering topology. So topology, these are deformation invariant degrees of freedom, or deformation invariant numbers associated to a geometry. You guys have probably seen before at some point the famous notion of a genus, the number of holes of a surface. By this notion, a coffee cup and a donut are the same object, because if it was made out of rubber, you could smoothly stretch or deform the coffee cup into the donut, and vice versa. So you can think about it that way. If the space was rubbery and you could just stretch it without tearing it or gluing it non-trivially, how can you change it so that it stays, what quantities can you not change in that process? So the answer in this case is, in fact, the genus, which is 1. That's the number of holes, right, in T2. That's a Calabi-Yau. This is the geometric invariant. First term class is 0. Geometric invariants in 2D and higher, we can start using the curvature to define some of those geometric invariants. And this is through what are called the Chern classes. And this is basically trace R, trace R wedge R, etc. I can write down various powers of the curvature and take the trace and ask what I get. I'm not going to prove for you that these are invariant under any deformations, but it turns out they are. In the case of K3, you can show that the first Chern class is 0. That's the Ricci flatness condition. The second Chern class gives you a unique number when integrated over the manifold. That's 24, and so on. There's also the number of moduli, the cohomology, the forms that we varied before. In this case, H1 of Tx dual. This is 20-dimensional. That's another topological invariant. So I can ask for the Calabi-Yau threefolds, what numbers can I use to show that two Calabi-Yau's threefolds are the same or different? So this is a theorem due to Wall. Wall argued that there are sets of numbers consisting of the Hodge numbers. Let me write these and then I'll explain what these are before. Second Chern class. So this is the Kähler deformations that I defined before. I wrote this as H1 Tx dual. These are the complex structure. I wrote this as H1 Tx previously. These are metric degrees of freedom, so the variations to the Kähler and complex structure. Those numbers characterize a Calabi-Yau threefold. The second Chern class, this is the trace of the curvature squared, and this guy is called the triple intersection number. Triple intersection numbers. These are if you have within your Calabi-Yau, if you count all the ways that hypersurfaces can intersect. So anything in codimension 1, if you look at the ways that independent codimension 1 hypersurfaces can intersect, if you take 3 different hypersurfaces in a 3-dimensional space, they will intersect at points. So this gives you a number of points in the space in X. And those numbers are also topological invariants. If you give me the set of these numbers, if these numbers are different between two Calabi-Yau threefolds, then it implies that CYs are distinct. And the converse is true as real manifolds. If they're the same, true as real, not complex. So let me say this. If these numbers, topological numbers, are different, the Calabi-Yaus are for sure different manifolds. If these numbers, this big vector of numbers, are the same, then two Calabi-Yaus are the same as real manifolds, but not the same as complex manifolds, necessarily. So this just gives you a handle. There are some numbers you can compute. You can say, for those numbers, can I figure out how many distinct Calabi-Yaus I have? And people have built vast data sets of Calabi-Yaus. So the largest is the case of using generalizations of the weighted projective spaces that I just defined for you. People have written down well over 500 million different algebraic descriptions of Calabi-Yaus, and they have computed subsets of this topological data, and there are definitely order of 1 billion distinct manifolds within that set. So there is a vast number of different Calabi-Yaus. And now we have the question, if I were doing heterotic string theory or any other type of string compactification, now that I have 500 million different background geometries, the effective theories I could write down would be highly constrained from each of those. But I would need to run through 500 million different calculations or more in order to figure out what theories I get. And these are just the algebraic ones we wrote down thus far. So this was what we knew how to construct. The question is this set finite? This is an open question, which has not been decided. So whether there's a finite number of Calabi-Yau threefolds is still open. But let me mention just one thing that is important. It has recently been observed that in terms of these methods of constructing Calabi-Yaus, even when I build Calabi-Yaus algebraically in this way, nearly all known Calabi-Yaus, and here I'm going to say greater than 99% of known Calabi-Yaus, are actually fibered in the way that I defined for you as a fibration. They are actually T2 fibers over surfaces for Calabi-Yau threefolds. So X has a projection over to some two-dimensional surface such that the fiber over it is a T2. These are called genus 1 fibrations. So essentially, all of Calabi-Yaus that we know of are genus 1 fibered. And this matters because there is a theorem due to Mark Gross and work by Antonella Grassi, which states that the number of T2 fibered Calabi-Yaus CY3s is finite. So this is kind of a remarkable fact. If you knew that your manifolds were fibered, then you know that there's a finite set of them. And it has only recently been observed that, in fact, everything we were building, no matter how we were building it, whether it was by these surgeries, algebraic constructions, appears to secretly already be a fibration too. So if we just understood how to build fibrations, perhaps we could have built all of those, in complete generality, we could have built all of those geometries a different way. This leads to the conjecture, is it possible that, in fact, every Calabi-Yau threefold, or nearly every Calabi-Yau threefold, must admit a fibration of this type? And if that was the case, there would be a finite number of Calabi-Yau threefolds. So this is an active, ongoing area of exploration. And let me state a conjecture on that front, just for fun. Oops, wrong one. That one goes up. Nope, that one goes up. There we go. Okay, so where did I put this? The conjecture is that every CY threefold with Hodge numbers scalar moduli, H11, remember that's H1 x tangent bundle dual. If this is greater than 19 degrees of freedom there, this will admit a T2 fibration. This matters for one other reason. So this matters, if this was true, you would be able to show that there are a finite number of pairs H11, H21. It has been proven that if you have elliptically fibered or genus 1 torus fibered manifolds, these guys can be bounded. And these, in fact, the largest pair that is possible is 11,491 if you have a T2 fibration. So these numbers would be bounded by above. And you could ask whether this could help you with finiteness of the entire data set. The other reason that this would play a huge role in terms of string vacua is when Calabi-Yau manifolds admit fibrations, this plays a really strong role in string dualities. So for example, I've been talking, up till this diversion on manifolds, I've been talking about heterotic compactifications. Any heterotic compactification on a threefold which has this T2 fibration will have a F-theory dual. This is strongly coupled type 2b in 4 dimensions. Likewise, if I have fibrations, K3 fibrations in type 2 theories, type 2a will have heterotic duals. Basically, any fibration of a Calabi-Yau has some notion of relevance for string duality. This tells you that there is a huge amount of redundancy in different string descriptions of the string vacuum space. So you could ask, in the 4D theories that I get, if essentially all heterotic theories that I could write down on Calabi-Yaus admit these fibrations, this means that nearly every heterotic theory that I could write down in 4 dimensions could also be realized in F-theory compactifications and so on. So in fact, the set of possible string vacua that I might write down from any method of string compactification may have been much more constrained than I thought.
Sorry,
Okay.
Question.
Yep.
Does the theorem and the conjecture also hold for Calabi-Yau fourfolds? Is there something similar?
Great question. So yes, it does. So let me actually give you, I meant to write this up. Let me give you 2 refs on that, some of which are related to fourfolds. So refs for, I'm doing this just briefly because I want to finish up with heterotic on this lecture, but to read more about why we think this is true, what the evidence is, and for threefolds and fourfolds, let me say see the following papers. So this is 1608, 07555, 1708, 07907. These two are about Calabi-Yau 3s. And this one, which is written by James, is actually the one that first made us interested in how ubiquitous fibrations are. This is about Calabi-Yau fourfolds, CY fourfolds. So here's some refs. Yes, the statement is we expect that essentially all known, well, it is a true statement that the vast majority of known constructions of Calabi-Yau fourfolds will admit a fibration. My expectation is as well that this is going to be toggled with Kähler moduli in the fourfold case. There are more independent Hodge numbers in the fourfold case, so you have to worry a bit more about what makes the fourfolds distinct. But again, the expectation would be there would be going to be some bound in topology beyond which you would expect everything is fibred. Other questions? Yeah.
But then you would also need a similar theorem that the Calabi-Yaus are really distinct. Right?
Absolutely. You would need the equivalent of Wall's theorem in order to check. It is known what the independent Hodge numbers are for Calabi-Yau, the independent topological data for fourfolds. It's very similar, Turing classes, Hodge numbers. Again, there's a one direction of that, which is that if the Hodge numbers are different, the manifolds are different. If the Hodge numbers are same, there isn't there is a natural analog of Wall's theorem, but to my knowledge, it has not been proven yet. So the question of when two manifolds are the same and different at a deeper geometric level is still open for fourfolds. Other questions? Yeah.
Could you say something about the geometry of B2? About
Great
the
question.
space?
Excellent. Okay, so that's great. So where did I put it? I think I moved it up already. So I mentioned that this, within the class of fibrations, it's known that the number of T2 fibered Calabi-Yau threefolds is finite. So the way that proof actually went was by characterizing properties of that base. So the way that Mark Gross did this. Unfortunately, it is a non-constructive proof. So you can prove that basically there is a simple starting point of just a couple of bases. I can write this down quickly. So what is B allowed to be? So B2, for those of you that have seen a little bit of Kähler complex geometry before, this falls in a very simple set. This can be Hertzebruch surfaces, Fn, the Enriquez surface, P2, and then here's the hard part, blow-ups of these. So you can start with simple Fano or almost Fano surfaces, and you can show that this is the condition you have to have for the bases, and then you start blowing up points. So you can get the Del Pezzo surfaces by blowing up points in P2. Depending on where you put those points, non-generic points, if you keep messing with those fibrations, it turns out that this blow-ups can become huge. So this work, I would say, work by Taylor and Morrison. They have characterized all toric twofold bases that can appear in Calabi-Yau threefolds, but for non-toric, this is still an open question. So we know that the set of bases is finite, but actually doing all these blow-ups explicitly and enumerating exactly how many and figuring them out, that has not been done. Other questions? Good. Okay, so with my remaining couple of minutes, what I want to now do is switch gears and say just a little bit more about geometry. So I wanted to give you a flavor of explicitly it's not so bad actually building Calabi-Yaus. It gets hard fast when you say how many there are and whether you can bound them. There's interesting progress on that recently. But the geometry itself is not the whole story, and it's actually crucial that we fold in the gauge fields that also arise in the heterotic compactification. So let me now turn to the way that the gauge fields enter the story and how they actually change the geometry that you want to enumerate. And I'll finish with that. Quite a lot of what I've mentioned today in these algebraic descriptions is, of course, extremely old. I should have mentioned, and I was rushing so I didn't, this simple algebraic construction in projective spaces was actually done for the first time in the 1980s by Philip Candelas when he was here at CERN. This was actually a feat of 1980s computing. So they did this on magnetic tape. They tried to generate all the Calabi-Yau's you could write down in simple products of projective spaces. There are 7,890 of them. And here at CERN in 1987, they wrote them all down. That was pretty cool. If you actually try and run that to generate all those manifolds, if you don't write the algorithm cleanly on a modern computer, it won't finish in your lifetime. So they were actually extremely clever to get that done in 1987 here. But there is a very old story to be told. Obviously, these have been around for many years. So I'm going to finish off with some newer stuff on how the bundle geometry talks to this whole problem. And then James is going to take you tomorrow through how we extend a lot of this stuff into the non-Kähler directions and more modern constructions as well. OK, so what I want to do is return to gauge fields. And observe that we don't just have to build Calabi-Yau's and worry about whether they're finite. We actually have to worry about whether there's a finite number of gauge fields over those Calabi-Yau backgrounds. And we have to ask, can that be bounded as well? So remember, we have to satisfy these equations. I didn't mention this earlier, but these, of course, have a name. These are the Hermitian-Yang-Mills equations. The key here for finiteness of a solution is this guy. This is the statement that the vector bundle is, quote, stable. And just intuitively, this means it has constrained substructure. It basically means that the bundle is sort of as irreducible as possible. So what do I mean by substructure? Bundles can be written, can be built in simple ways. So let's just think about how to build a gauge field. So let's say I was doing a U1 theory. The gauge degrees of freedom that I have to keep track of over my Calabi-Yau would be a single complex number at each point. So that's a copy of C at each point in X. If I can ask how many different U1 gauge fields can I write down over the manifold, it turns out that U1 gauge fields on a Calabi-Yau are classified by their first Chern class, trace R. So you can actually parameterize this in terms of the Kähler moduli. For example, on P45, this is written OM, for example, is a line bundle, U1 gauge field, one complex line over each point. This is the thing that has first Chern class, C1R is M times the Kähler form. C1 of V, not R. C1V, which is the trace of the curvature. So line bundles, here I can write down an infinite family of them. You could ask, for a given vector bundle, how many line bundle subbundles are there, how many rank 2 subbundles, and so on. And stability is about getting things that have very few subbundles. I'm not going to get into the details of that just yet. But the interesting thing is that if you have stable bundles, then you have bounds on topology. Okay. So if you solve these equations, then we can ask, can we bound the topology? So if we solve Hermitian-Yang-Mills, can we bound topology of the gauge? And the answer is yes, you can. So the independent Chern classes are C1, C2, and C3. These are the Chern characters, if you want. This is the traces of the curvature. It turns out in heterotic theories that C1 of V must be 0. This is the condition to have spinors in space. Recall that we saw CH2 of the bundle the second Chern character. This is the trace of the curvature squared. We saw this already in an anomaly cancellation condition through the Bianchi identity. Remember, we saw dH was trace R wedge R minus trace F wedge F. In heterotic theories, even when you include non-perturbative constraints, this amounts to the condition that C2 of your vector bundle, or CH2 of your vector bundle, has to be less than C2 of the tangent bundle. That's what this condition tells you. And C3 of the bundle, the trace of curvature cubed, this guy is, in the 4D theory, this is actually the chiral index. So this is the number of generations, number of gens minus antigens. Sorry, this is a bit hard to read down here. Yeah. Try and write up here, make that more legible. So this is actually telling you about the number of degrees of freedom in the 4D theory. So it's telling you families minus anti-families in the 4D theory. What can you say about all these? So there is bounds on 2 bits of those topology, and happily there is a theorem. That's not the right one. Yep. Sorry, I wrote number of gens minus antigens. So generations of matter. So for example, in an SU5 gauge theory, this would be the number of 5s minus the number of 5 bars. Okay. So theorem, this is due to Maruyama and Langer. They have proven that if V is stable, i.e. if it solves those Hermitian-Yang-Mills equations that I wrote down, and C1 and C2 fixed, then it turns out there is a finite number of C3s. So this tells you about the structure of the heterotic theory that the topology is constrained. So within a heterotic background, I cannot have an infinite number of generations of matter in my theory. It must be finite. This is, again, a non-constructive proof, unfortunately, so you don't know quite how many you're allowed for any Calabi-Yau compactification. But there'd be a finite range of topologies. And moreover, there is also a proof that there are a finite number of components to M bundle moduli space for fixed topology. So the moduli space of stable bundles, if you fix the topology for me, will have finitely many components. So there will be a finite number of bundles to count on any given Calabi-Yau. Again, remember, just like the Mobius strip and the cylinder example, you give me a compact space, I'm not allowed to write down just any gauge fields. I'm only allowed to write down gauge fields for which I have sensible gluing as I move around those cycles. So in the S1, there's just one connection point in the S1 where I have to glue the fibers together. I either give them a twist, that's Mobius strip, or I glue them together straight, that's the cylinder. Likewise, for these fibers in the gauge fields, they can be very complicated, large dimensional spaces. As I move around the manifold, I have to glue them together. There's a finite number of ways to do that and a finite bit of topology. Okay, to conclude, what I want to show you is that this topology can really matter in terms of the degrees of freedom in the theory. So if you have a bundle, it's tempting to think I have a 500 million different Calabi-Yaus, I have some finite but unknown large collection of bundles over them. I could just pick any 2 out of a hat, write down some theory, and ask, what do I get? In fact, those 2 components can talk to each other in very meaningful ways. So I just want to give you a quick hint on this, and then James will take this further and extend it to the non-Kähler case tomorrow. I want to look at the ways that X and V couple. And specifically, I want to look at the moduli. So the moduli are the smooth deformations of those pairs. Remember that I said loosely before that the scalars in the 4D theory, these were counted by the Hodge numbers H11 and H21 of the Calabi-Yau. Again, mixing notation for you. These were the Kähler and complex, so Kähler, complex structure, degrees of freedom. And I also mentioned there were degrees of freedom from the bundle. These are singlets, fluctuations of the gauge field that were counted by H1, X, and 0V. So these are what we called the bundle moduli before. And I listed these as if they were three separate quantities that I could compute, and those are the scalars of the theory. But that actually is a little bit naive, as I want to show you. So when we consider these equations of motion, we don't actually get to fluctuate the metric and the gauge field independently. You have to actually fluctuate them at the same time and ask, how does that happen as a geometry problem? So let's go back to those equations of motion. One more time, let me write these guys up. So what happens if I allow delta G and delta A simultaneously? What can I say about those degrees of freedom? So before I argued for you that these guys, the bundle moduli, these were the closed one forms that I got of d bar delta A being 0. These I got from plugging in a fluctuation to this equation and watching what happened. I just said, plug in the fluctuation, see what you get. However, I kept the metric fixed. Specifically, I kept fixed the notion of barred and unbarred coordinates when I wrote that down previously. What if I hadn't done that? What if I allowed things to fluctuate at the same time? So you can actually see that these fluctuations will exist, and they can give you non-trivial obstructions from a four-dimensional moduli space point of view. Specifically, they can appear as obstructions in the four-dimensional superpotential, which can tell you that not all simultaneous fluctuations are allowed. So you can see, let me do this from the equations of motion first, and if I have time, I'll come back to the superpotential argument. So I want to do this fluctuation again from the point of view now of not assuming that I'm holding the metric fixed. And I want to allow, so let's look at f a bar b bar equals 0. I want to consider delta A now and delta G. And to do that, because I've already written this in complex coordinates, and as the metric changes, this will vary, let me actually write this in real coordinates. So I can introduce projection operators, Pij, in terms of the complex structure. In real coordinates, P bar ij. If I introduce these projection coordinates with j squared, remember, as -1, then I can rewrite this equation in terms of real coordinates as follows. There's 2 and one more. P bar ji, P bar lk, f jl equals 0. So these three actually take the place of one much more simple equation in complex coordinates. If I write this all in real coordinates, what I can now consider is a fluctuation of the complex structure, allow j to vary, and allow the connection to vary at the same time. And let's see what we get. Okay. So I want to consider perturbations. Oop. Sorry, a better squeegee. I'm going to make this unreadable if I'm not careful. try that again. So we want to consider perturbations of the following form. Let's consider J goes to J plus delta J, and the gauge field fluctuates as A plus delta A. And now I want to ask about simultaneous deformations and what they satisfy. In the interest of time, you can rewrite things, instead of writing those real coordinates over and over again, I can write things in terms of complex coordinates. So it turns out that in terms of complex coordinates, I can write delta J B bar A as the following. This guy is a basis of complex structure fluctuations, and this is the actual complex structure. So these would be a set of fluctuations. Here this runs, I runs 1 up to H to 1 of the manifold. If I write that in this way, I can show that those 3 equations I wrote down to first order give me the following. And this is not so bad, so this is why I want to write it out in detail. Okay. So why did I bother to write this out for you? It turns out that the first order fluctuation of that equation, allowing complex structure and gauge fields to vary simultaneously, actually isn't too bad a form. And it's easy to understand what happened here. This complex structure contraction acting on your original field strength says you can fluctuate the field strength in such a way that what started off as a 2-0 piece, so remember this guy was 0, this is a 2-0 or 0-2, depending on your notation, component of the field strength. What was, in this case, a 1-1 piece can be rotated into a 0-2 piece. So here I'm rotating something that was a safe component of the field strength into the part that's supposed to be 0, and that can be compensated by some change of connection which is not d-bar closed. If I turn off the variation in complex structure, so set delta z to 0, then I'll be left with just the constraint I had before, namely that the fluctuations of the connection have to be d-bar closed. And if I turn off this guy, I will be left with the condition that this fluctuation, this fluctuation has to vanish in order for this to be still a holomorphic gauge field. So I can see that from this equation, in principle, I could have all the bundle moduli that I had before, but the complex structure of the base manifold and the fluctuations of the connection through an equation like this could actually talk to each other. So I want to explore a little bit about what that means. It means that what I thought of as independent moduli, here I've looked at just H21 and the bundle moduli H1 and 0V. We thought of these as 2 separate degrees of freedom, base and fiber degrees of freedom from the gauge fields. But if you actually allow everything to vary simultaneously, they are constrained against one another. So the statement that is important is not every delta z can be balanced by a delta A. So what that means is that if you want to allow the manifold to deform, not all complex structure moduli are true moduli of the theory. So what you thought of as metric degrees of freedom in your base are actually being fixed by the presence of your gauge fields. So let's phrase this again. Adding V can freeze or lift moduli of X. This is an important problem in terms of the massless scalars of the 4D theory, because it means that you have less than you might have thought in the beginning. And it's also important because it tells you that certain bundles can only be compatible with very special manifolds. So just to finish up, I think I've got like 5, 10 minutes? 5 minutes, probably. You guys want lunch. I see it in your faces. OK, 5 minutes. Let me just conclude by saying that there are 3 geometric objects that I want to consider. So deformation problems in geometry, there are three things I could have considered mathematically, and it turns out that in the physics literature, for about 20 years, we were considering the wrong one. You can consider deformations of X itself as a complex manifold. Those are wiggles of the complex structure. These are changes of the shape of the complex manifold. So just like the donut in the coffee cup, that's changing which configuration you're putting it in. These are counted to first order by, as we've discussed several times, H1Tx, one forms valued in the tangent bundle that are d-bar closed, H21. These are the moduli of X. So deformations, defs of X as a complex manifold. Complex manifold. You can consider deformations of the bundle. This is what I've referred to as bundle moduli so far. These are counted by what were the bundle moduli. These are just the d-bar closed guys, so this is just the d-bar delta A condition. These are variations of the bundle holding the base manifold fixed. But geometrically, what we actually want to consider are deformations of the pair. That's what we've just seen. And we can ask what parameterizes their first order deformations. And it turns out that geometrically, this was actually studied by Atiyah in the 1950s. There is a description of some bundle, H1X, let me call it Q. So some one forms valued now with some particular gauge fields, gauge indices valued in Q, which looks like the following. It looks like a non-trivial combination of the adjoint valued gauge fields. That's this N0V. This is adjoints. What is this? This is a combination of the tangent bundle and the adjoint valued gauge fields. These arrows in this sequence, this is what's called a short exact sequence. And I'm out of time to define this properly for you, but let me just say that this means that this is almost, let me write it this way. If I write anything with these arrows, A goes to B, goes to C, goes to 0, what this is, the statement is that B is almost the direct sum of A plus C. And the degree to which it is not just a direct sum, to which those pieces are non-trivially glued together, can be measured. And basically, the connections look like A of C, and then something off diagonal. That's what these short exact sequences look like. So there is a connection which glues together non-trivially the gauge fields and the tangent bundle over the manifold. And this is the geometric object that you actually want to study those first-order deformations. Why am I mentioning this? Because this type of structure, here the gauge fields are actually talking to the base. You have to consider a simultaneous deformation problem. In the case of heterotic compactifications, this gives you a very different count for the number of moduli. So you can ask, how different is that count? It turns out that you can consider bundles and ask how many of their base moduli can be constrained. So imagine that you have the base, you want to wiggle it like it's made out of rubber. You consider the fibers over it, and you say, how do those fibers, which fibers can come with me as I do those wiggles? It turns out that for very simple, even SU2 bundles, so SU2 gauge theories, you can actually fix all of the moduli of the base. So you can create entirely rigid base manifolds. You can freeze out metric moduli doing this. This changes the moduli count dramatically, and this is an example in heterotic of that. This will happen in other string compactifications as well anytime you have fluxes. So you can consider deformation problems mathematically. This is the deformation problems of gerbs. But this type of coupling of some form, here it's a gauge field in the metric. If you have 2 forms, 3 forms appearing in type 2 theories, then those will also couple non-trivially to the metric, and you can view it in a similar way. So to conclude, why are you interested in this? This tells you that, in fact, the types of geometric objects you want to characterize are not necessarily just the bundle and the manifold separately, but in fact, these combinations which can be deformed. So you can ask, from the point of view of these fibrations, could I actually characterize the total space? So remember, in our Mobius and cylinder example here, we talked about a U1 gauge theory over S1. If I consider arbitrary vector bundles X Calabi-Yau, and here these are V gauge over them, I can ask what set of total spaces do I actually want to enumerate, and can I work out the physics of those? So I will actually pause here and let you guys go to lunch. James is going to tell you more about this total space structure and some recent results in that, including in the non-Kähler case tomorrow. Thank you.
Does the short exact sequence naturally extend to the long exact sequences of the topology groups?
Absolutely, and I was going to show you that, and I ran out of time. So if you'd like to see me after, and I can show you how. So it's actually possible by writing down the long exact sequence in cohomology, you can reproduce exactly this constraint. So you can see that the Atiyah class here, yeah, it exactly works out to do the right thing for you.
In mentioning freezing, you touched on what I wanted to ask about. If you think of moduli fields in a lower dimensional theory as integration constants of the background solution, which you then allow to be dependent on the lower dimension. Not all of these are interesting in the sense that some of them end up with only first-order differential equations and they freeze out.
Absolutely.
For example, an M2 brane is just the charge of the M2 brane because of the Yankee identity of the form field kills that modulus. Is there a general litmus test for interestingness of or freezing out as well?
That's a great question. So, I mean, there's all sorts of directions you can take that. So one question which is sort of related is to what Kelly was just asking is we also have orders in deformation theory, right? So in terms of the field theory, you can consider fluctuations around vacuum to various orders. Frequently, the first order deformations will be lifted to higher orders, so non-trivial interactions in the superpotential will lift degrees of freedom. What I'm describing here is actually even the first order result. So it's even the first order is not what you thought it was. I think the straight up answer is that this is hard to see. I mean, basically what has tended to happen in the literature is people have just written down naive combinations of things without doing the full fluctuation problems carefully, and you can get it wrong. So in the heterotic literature, it was wrong for about 20 years. People didn't realize that you should be counting different combinations of moduli. If you add in non-perturbative effects, you got to count this now, taking into account all of those degrees of freedom as well. And there's some pretty geometry. You could do this adding in M5 branes geometrically as well in heterotic, and can you model that? So there's great questions, but yeah, the short answer is no. I don't think there's an easy way without doing the full calculation to know what's going to be a good modulus of the theory and what is not.
Any other question? If not, let's thank Lara again.